We are in section 11.4, the comparison test. The idea behind the comparison test is to compare a given series with a series that is known to be convergent or divergent. So this is another test that we are available to use now. And so the comparison test says, suppose that the sum of b sub n is a series with positive terms. Then, 1, if the sum of b sub n is convergent, and a sub n is less than or equal to b sub n for all n, then a sub n is also convergent. 2 says that if the sum of b sub n is divergent and a sub n is greater than or equal to b sub n for all n, then a sub n is also going to be divergent. And so again, divergent and convergent, but you also need to look at what you're comparing it to. And we have some examples right below this. The first one says, determine whether the series is convergent or divergent. And again, make sure to state which test you are using. So part A says the sum from n equals 2 to infinity of n cubed over n to the fourth minus 1. And for this, I noticed that if that minus 1 wasn't there, this would be a lot easier to deal with, and that would simplify really nicely, and would simplify to 1 over n, which I remember from seeing in a previous section that that's just a harmonic series. So let me see if I can compare it to that. So I'm going to let a sub n equal my original function that we have, the series that we have, which is n cubed over n to the fourth minus 1. And I'm going to compare this to a simplified version of this, which is going to be n cubed over n to the fourth. And that simplifies to just 1 over n. And so now comparing a sub n to b sub n, I noticed that if I were subtracting 1 and then dividing by that, that would actually make a sub n be larger. So this is going to be greater than or equal to b sub n. And we know that the sum from, and we're dealing with n equals 2 to infinity of my b sub n here, which is the sum from n equals 2 to infinity of 1 over n. This is going to be divergent. And it diverges because it's a harmonic series. So again, make sure you state the reason why. If it's a test, this is by definition of a harmonic series. And therefore, since we know that b sub n is going to be divergent, if you look right up above, if it's divergent and a sub n is greater than or equal to b sub n, which is our case for part A, so therefore we can say that the sum of our original n equals 2 to infinity of n cubed over n to the fourth minus 1 is also going to be divergent. And we can say also, and this is because a sub n is greater than or equal to b sub n, and the sum of b sub n from n equals 2 to infinity diverges. And this is going to be by our comparison test. So again, making sure to state a reason why anytime you say it converges or diverges. So part B says the sum from n equals 1 to infinity of n minus 1 over n squared square root of n. And so again, I noticed that that minus 1, if that was gone, that would have simplified very nicely. So I'm going to go ahead and look at this and let a sub n equals my original, which is n minus 1 over n squared square root of n. And b sub n, I'm just going to ignore that minus 1 and say if we had n over n squared times the square root of n, or n to the 1/2, this would simplify to being, you can simplify one of those n's and you'd have 1 over n times n to the 1/2, or 1 over n to the 3 over 2. And we can look at this. And if you notice, if you're subtracting 1 from the numerator this time, that actually is going to make it smaller of a value versus in part A where the minus 1 was in the denominator. So subtracting 1 from the numerator makes it smaller, so a sub n would be less than or equal to b sub n. And now let's go ahead and look at our sum of b sub n. So the sum from n equals 1 to infinity of b sub n, which for this problem is going to be the sum from n equals 1 to infinity of, and it's 1 over n to the 3 over 2. And so this is a p-series test that we can use. And so we know that p is equal to 3 over 2, which is greater than 1, which means that this is going to converge by p-series test. Therefore, looking up above, if we know that b sub n is going to be convergent and a sub n is less than or equal to b sub n, we can also say that the series for a sub n is also going to be convergent. So therefore, the sum from n equals 1 to infinity of the original problem that we had, which is n minus 1 over n squared square root of n, converges also. And this is because a sub n is less than or equal to b sub n, and the series, our b sub n, converges. And this is by the comparison test. Part C says the sum from n equals 1 to infinity of 6 to the n over 5 to the n minus 1. And I'm noticing that in the numerator and in the denominator, they're both a value raised to the same exponent of n. And so it reminds me of a geometric series, but again, I have that minus 1 in there. So I'm going to go ahead and write down a sub n equals 6 to the n over 5 to the n minus 1. And I'm going to compare this to b sub n, which I'm going to ignore that minus 1 again and simplify this and say 6 to the n over 5 to the n, which is the same as saying 6/5 raised to the nth power. And so looking at this, since the minus 1 is in the denominator, I'm subtracting it. I know that a sub n is going to be greater than or equal to b sub n. And then looking at the sum from n equals 1 to infinity of b sub n, which is the sum from n equals 1 to infinity of that 6/5 to the nth power. This is a geometric series, and r is equal to 6/5, which is greater than 1, which means that this is going to diverge. And it's diverging because of the geometric series test. So by And so from here, we can look at this and notice that since b sub n is going to diverge and a sub n is greater than or equal to b sub n, as stated up above by the comparison test, we can say that the series that we have, the original one, is also going to be divergent. So therefore, the sum from n equals 1 to infinity of 6 to the nth over 5 to the nth minus 1 diverges also. And this is because a sub n is greater than or equal to b sub n, and our series from n equals 1 to infinity of b sub n diverges. And this is by the comparison theorem. So part D, I'm going to circle and we'll look at that one together in class. At the top of the next page, it says the terms of the series being tested must be smaller than those of a convergent series or larger than those of a divergent series. If they are not, then the comparison test does not apply. In these cases, the following limit comparison test can be used. So the limit comparison test says that suppose that the sum of a sub n and the sum of b sub n are series with positive terms. If the limit as n approaches infinity of a sub n over b sub n is equal to c, where c is a finite number, And if C is greater than 0, then either both series are going to converge or both diverge. So the example right below this says determine whether the series is convergent or divergent. And so again, I have the sum from n equals 1 to infinity of 1 over 2 to the n minus 1. And again, that minus 1 is an issue. And so I'm going to go ahead and say that a sub n is my original. And comparing it to b sub n, which would be a lot nicer if that minus 1 was not there. So I'm going to say 1 over 2 to the nth, which is the same as saying 1 over 2 raised to the nth power. And so we know that the sum from n equals 1 to infinity of b sub n, which is going to be the sum from n equals 1 to infinity of 1/2 to the nth power, r is equal to 1/2, which is less than 1. So that means this is going to converge by the geometric series test. And comparing my a sub n to my b sub n, since we were subtracting 1 from the denominator, a sub n is going to be greater than or equal to b sub n. But looking back at your comparison test that was on the previous page, you'll notice that because this converges, I would need to have a sub n less than or equal to b sub n in order to state that it also converges based upon the comparison test. So we can't use comparison test. And this is because a sub n is greater than or equal to b sub n, and b sub n converges. So again, we're stuck, and like it states up above, when you are unable to apply the comparison test, then next thing to try is the limit comparison test. And so that's the limit as n approaching infinity of a sub n over b sub n. And we're going to see if it equals a finite number, and if that finite number is greater than 0, then either both series converge or diverge. So looking at that limit, we have the limit as n approaches infinity, and it's a sub n over b sub n. And so we have the limit as n approaches infinity of a sub n, which is 1 over 2 to the nth minus 1, all over b sub n, which is 1 over 2 to the nth. And from here I can rewrite this, multiply by the reciprocal of the denominator. And so I have the limit as n approaches infinity of, and it's going to be 2 to the nth over 2 to the nth minus 1. And thinking about this a little bit, I noticed that 2 raised to the nth power as n goes off to infinity would also be infinity. And so I would have infinity over infinity. And so this is indeterminate. So simplifying this, I can have the limit as n approaches infinity, and I'm going to go ahead and multiply both the top and the bottom by 1 over 2 to the nth. And doing that, it's going to simplify this a little bit, and I'm going to end up with 1 over 1 minus 1 over 2 to the nth power. And taking the limit of each of these terms, the limit as n approaches infinity of 1 is just 1, and then the limit as n approaches infinity of 1 over 2 to the nth is going to be 1 over infinity, which means it's going to be approaching 0. And so this is going to equal 1 over 1 minus 0, or just 1, which is a finite number, and it is greater than 0. So yes, C is greater than 0. And so we're able to use that limit comparison test. And so again, the limit comparison test says that if C is finite, and since C is equal to 1, and this is finite and greater than 0. Then we can also say that our original series would be convergent because of the limit comparison test. So therefore, since the sum from n equals 1 to infinity of b sub n converges, then the sum of my original one, which is going to be n equals 1 to infinity of 1 over 2 to the n minus 1, converges also by the limit comparison test. So part B, right next to this, I'm going to go ahead and circle, and we'll look at this one together in class. At the top of the next page, it says estimating sums. It says recall in 11.3, estimating sums r sub n, which was also called our remainder, is equal to s minus s sub n, which is equal to a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, and so on. We will now be estimating sums for the sum of a sub n and the sum of b sub n. Since a sub n is less than or equal to b sub n for all n, we have r sub n is less than t sub n, where t sub n is equal to t minus t sub n, which is equal to b sub n plus 1 plus b sub n plus 2 plus b sub n plus 3, which is less than or equal to the integral from n to infinity of b sub n dx. So the example right below says use the sum of the first 10 terms to approximate the sum of the series. Estimate the error. And so we're going to go ahead and look at the first 10 terms. And so in order to do this, I'm going to make a table just to kind of organize my data. And this is going to be n in the first 10 terms. And then we're going to look at a sub n. And our a sub n is given to us right here. It's sine squared n over n to the third. So this is our a sub n. And so using a calculator, we get the first term to be 0.7081. Substituting in 2 for our second term, we get 0.1034. Substituting 3, we get 7.4 times 10 to the negative fourth. And then continuing this on to get the remaining values. And from the calculator, we get those remaining terms. And so use the sum of the first 10 terms to approximate the sum of the series. Estimate the error. So as stated up above, we're going to compare this to a simplified version of a sub n. And I'm going to go ahead and look at b sub n. And we know that since a sub n is equal to sine squared n over n cubed, and we know that sine squared n is going to be in the interval from 0 to 1, since sine is normally in the interval between -1 to 1, but since we're squaring those values, they will just be the positive ones. So going from 0 to 1 and including both 0 and 1. And I'm going to compare this to b sub n. And I'm just going to say b sub n, since sine squared n cannot be larger than 1, we'll say 1 over n to the third. And so we know that a sub n is less than or equal to b sub n. And then we know that r sub 10, that remainder, is going to be less than or equal to t sub 10. And as stated up above, we know that this is going to be less than or equal to the integral, and it's going to be from n to infinity of b sub n dx. And so n for this problem is 10 to infinity of b sub n, which is going to be 1 over n to the third. and dx. So I'm going to go ahead and rewrite this with a variable of x instead of n. And so we're going to have x to the third dx. Rewriting this as the limit as I'm going to use t approaches infinity of the integral from 10 to t of, and I'm going to rewrite this as x to the negative third dx. And then I have the limit as t approaches infinity, adding 1 to my exponent and dividing by that same value, I get negative 1/2 x to the negative second, evaluated from x equals 10 to t. And so we're going to have the limit as t approaches infinity of, and rewriting this, it's the same as negative 1 over 2x squared. And so we're going to have negative 1 over 2t squared minus, and then substituting in 10, I have negative 1 over 2 times 10 squared. And first thing to note is that the limit as t approaches infinity of negative 1 over 2t squared, as that denominator gets larger, this limit is going to go to 0. So this will equal 0. And so we have 0 minus negative 1 over, and then 2 times 10 squared will be 200. And so this equals 1 over 200. And so this value that we have here is our error. And then in addition, we can estimate this sum from n equals 1 to 10 of, and it's sine squared n all over n to the third by adding up all of our a sub n terms here. And so our sum is approximately equal to 0.83278. We're going to go ahead and look at part B. And for part B, we're going to do exactly the same thing. I'm going to make another table here. It says the first 10 terms. And so go ahead and write n and a sub n. So n going from 1 to 10. And substituting in 1 into our formula, we get 0.1429. Substituting in 2, we get 0.04. Substituting in 3, we get 0.01099. And continuing this and plugging in the remaining numbers. And so we get the remaining numbers by using our calculator. So now we're going to compare it to another function. I'm going to go ahead and look at a sub n, which is equal to 1 over 3 to the n plus 4 to the n. And so I'm going to think about this instead of, and letting b sub n equal 1 over 3 to the n plus 3 to the nth. And this would be the same as 1 over 2 times 3 to the nth power. And since 4 to the nth would be larger than 3 to the nth, since n is going to be a positive value, I could say that this would be less than or equal to. So a sub n is going to be less than or equal to b sub n. And we know that r sub 10 is less than or equal to t sub 10, which is less than or equal to the integral from 10 to infinity of b sub n. And I'm going to go ahead and write my b sub n in terms of x's. And so I'm going to have 1 over 2 times 3 to the x dx. And rewriting this as a limit, and I'm going to use t approaches infinity of the integral from 10 to t of 1 over 2 times 3 to the x dx. And that 1/2 you're able to pull out in front of the integral. And so we have now the limit as t approaches infinity of 1/2 times the integral from 10 to t. And I'm going to rewrite this as 3 to the negative x dx. And so we have the limit as t approaches infinity of, and with integrating this, we end up with 1/2 times 3 to the negative x times 1 over ln of 3, and then times the derivative of that exponent, which would be -1. So I'll put that negative out in front. And we're evaluating this from x equals 10 to t. And so from here, we have the limit as t approaches infinity of our function. I'm just going to combine that all together a little bit more. And it's -1 over, and if you notice that 3 would move to the denominator since that was a negative exponent. And so we have 2 times 3 to the x times ln of 3. And again, evaluating this from x equals 0 to t. And so we now have the limit as t approaches infinity of -1 over 2 times 3 to the t times ln of 3 minus, and then substituting in 10, we have -1 over 2 times 3 to the 10th times ln of 3. And looking at this limit that we have right here, you'll notice that the exponent is going to cause that 3 to get really large. And so that large value would be going off to infinity, but in the denominator, which means that this would be equal to 0. And so we now have 0 plus 1 over 2 times 3 to the 10th times ln of 3, which is our error, which is equal to 7.7075 times 10 to the -6. And we can also say that the sum from n equals 1 to 10 of 1 over 3 to the n plus 4 to the nth, if we were to add up those 10 terms here, we would get 0.19788. And again, over here we calculated that error that we would get.